Okay, we're now back to our old friend stoichiometry here, and we've done stoichiometry a variety of ways. We've done it by mass, where we used the molar mass. We've done it with gases, where we used the molar volume to get back and forth. We've also used aqueous solutions where we use molarity, and this is another case of aqueous solution, so we'll be using our moles per liter to help us out. Before we get into the tough stuff, the number stuff, let's just talk about how these reactions happen. One saying that often gets uttered in a chemistry class, that when we mix an acid and a base, we get a salt and water. So it's not always going to be sodium chloride, and as you may recall, that salt is just an old-time word that literally means any old ionic compound. So here's a bunch of acid-base reactions. So hydrochloric acid and sodium hydroxide first here. It looks like I've got positive and negative partners, so this should be just a partner trading. So hydrogen will end up with hydroxide, sodium ends up with chloride, and literally when I write out acid-base reactions, I write them out this way. I know I should probably write water as H2O, so if I was actually sharing this with some of my chemist friends, I might erase the HOH and write water, H2O. But just for bookkeeping, it certainly doesn't hurt to when you're trying to remember how the reaction is happening. Likewise, for the nitrous acid and potassium hydroxide, potassium and hydrogen switch partners, so I get potassium nitrite and water. Barium chloride works, or barium hydroxide and hydrochloric acid work the same way. We get barium chloride and two HOHs. Notice that we need two H plus ions for every two hydroxide ions that the barium hydroxide is supplying. And likewise with the sulfuric acid, we need two hydroxides to balance out those two hydrogens. So that's how those reactions end up in terms of their partner trading. And yes, each of those ionic compounds would taste salty, but I can't say that I would recommend any of them other than maybe the sodium chloride. Okay, now we're to the stoichiometry, and you guys all know how to do this. Just basically filling in the data as we find it here. I know that my top line is going to be my volume in liters. Next line down is the concentration in moles per liter. Then I'd have my mole line. Then I would have my coefficient line. So let's fill things in. I've got 0.25 mole per liter sodium hydroxide. So I have to put it in the right column. I've got 20 milliliters, so I'm going to put that for the hydrochloric acid, and it is 0.3 moles per liter. So I'm going to put that in next. So it looks like I've got enough information to calculate moles in that first column with hydrochloric acid. And if I look at the units, I can see that liters times moles over liters, so multiplying will get me to my moles. And once I've got that, I want to compare between two things, so I'm going to need the coefficients. It turns out it's 1 to 1, so that means that whatever the moles were for the hydrochloric acid, it's going to be the same for the sodium hydroxide. I could go through the process of dividing by those coefficients, but I could just transfer that moles over since it's a 1 to 1 ratio. So now I've got moles and moles per liter. I just need liters. So we multiplied going down, so that means going the opposite direction, I'm going to divide up. And I do that, and I get 0.024 liters, or 24 milliliters of sodium hydroxide is what I would need to neutralize that hydrochloric acid solution. Okay, here's one that isn't a simple stoichiometry, at least not so simple. I've got a 1 to 2 ratio here, so I'm going to fill in the data as I find it. I've got a barium hydroxide solution, and I'm going to use 10 milliliters of that, so I'm going to turn that into liters by dividing by 1,000, so 0.01 liters. And I know that I've got 32 milliliters of the acid, so 0.0320 liters, and its concentration is 0.150 moles per liter. So let's see, moles per liter times liters gives me moles, so if I multiply those two things out, I get that number of moles. And when I fill in my coefficients, I see that they're not the same. If they're not the same, I just can't transfer the moles over. So in order to kind of level things out, I've got to divide by the coefficient, bring that over, multiply up. I've got moles, I've got liters. So I want units that have moles over liters, so I'm going to take the 0.0024 moles and divide by 0.0100 liters. And I get 0.240 moles per liter. Not terrible. And that's about it. I've got 2 examples here, and that should be pretty much the kind of breadth of the type of reactions you're going to see. So we'll do more practice, I imagine, in class.